Okay, the question today is diagonal eigenvalue. So basically, consider a 30 times 30 matrix A with aii equals 30 for I from 1 to 30 and aij equals 1 for I does not equal to j. So let lambda equal lambda 1, lambda 2 be the vector of distinct eigenvalues. Lambda 1 does not equal lambda 2 of A, and g equals g of 1, g of 2 be the vector of geomultiplicities corresponding to lambda 1 and lambda 2 respectively. Find lambda plus g and then um, that, take that squared. So that's basically like the distance. Okay, so we set up so like the first approach to this question is that we know that we have a matrix and we want to find eigenvalues. So then my approach is just using the same as last video. If I want to find the thing, then I would you basically do the characteristic equation, determinant of A minus lambda I times I is equal to 0. So then if I do it like that, I get my determinant is equal to all of the things over here is still 1. And on the diagonals, we have all 30s. So then if we minus lambda I, it would just be all x's, which x means 30 minus lambda in this case. So we have this expression. So the problem is that we don't know how to simplify this further with Gaussian elimination. If we do Gaussian elimination, it would turn out to be a mess. So a trick that we can do is that we realize that every column sums to the same. Like every column sums to the same, every row sums to the same. So we're just gonna say that the rows are all the same. So then what we can do is for the columns, we can set the first column to be the sum of all the columns. So that in this case, we would have x plus 29 for each of the values inside column 1, and everything else stays the same. And this doesn't change the eigenvalue because we are just doing a column operation, and then we're just keeping the first row the same and adding other columns, which would not affect the value. So then we see that everything over here is x plus 29. So that means we can factor it out over here. So that's independent outside. So then when we factor it out, everything in this column, becomes 1. So that's a lot easier for us to manage because now if we realize that the first row, we finally got this to be 1, whereas everything else is x. So then everything with 1 means that we can just subtract the first row from every row. So then that would make us make like what is it called? A triangle over here. We would have the lower triangular form that we want to get into. So that everything here would be x minus 1 on the diagonal because x minus 1 is x minus 1. And everything that's 1 minus 1 is 0, so there's nothing left over here. So everything inside this triangle is 0. So then we have an upper triangle. So if we have an upper triangle, we know that basically everything on the diagonal would be our eigen eigenvalues. So then x minus 1 would be our eigenvalue here, and also 1 here. So we have 29 values which are the same, x minus 1 and one value that's 1. So here we see this determinant is equal to this form. So then we want to substitute it back because x was replaced for 30 minus lambda. So we get 30 minus lambda plus 29 is equal to 0. So we know that our lambda is 59. And our second term is 30 minus lambda minus 1 equals 0. So then our lambda would be 29. So then the 29 has multiplicity, I can't even pronounce it. Okay, so basically one has 29 of them and one has one of them. This is one approach of doing the problem, the classic way. I think the difficulty with this solution is kind of thinking about this property, the trick of adding all columns to column 1. I think that was like the major breakthrough that I wasn't able to do when I was doing this question. The second approach to doing this question involves another trick. It's just to see that the matrix by itself is equal to 29i plus j. So basically what it does is that we assume that there's one matrix where everything inside is one. That's the J matrix. And then we add this to a I matrix where everything on the diagonal is one. So then basically every term inside the diagonal that's 30 is just 1 plus 29. And then so on and so forth. And every other term is just 1 from this original matrix. So that's why we can write A as 29I plus J. So once we do that, we kind of see, okay, great, it's this way. And then we have the, yeah, I just explained the diagonal and off diagonal. So it matches the AII and AIJ given in the problem. So next step is looking at the eigenvalues. So basically, the eigenvalues of A are simply eigenvalues of J shifted by 29, because we were just changing with the I matrix. And then since J consists of all ones, it has a rank of 1. That makes sense because if we imagine a matrix of all ones, if we do Gaussian elimination, every row below the first is 0, so then it only has rank 1. So that means the no space is 29, so geometric multiplicity is 29. And then the remaining is just the 1. So then that has geomultiplicity 1. So that's where we get the 29 and the 1. Hmm, I'm still trying to work out how exactly we can get the eigenvalue, because I'm not sure. We should double check on that. Hmm. Okay, so I figured that little part out of the thing I'm not sure about. So basically the idea here is it still uses the same idea of like the row, like the sum of the row is the same. So what we do here is, why does adding 29i simply shift the eigenvalues? So basically what I found out was that we have a definition. By definition of just like eigenvector and eigenvalue in general, JV is equal to mu V, where one is the V is eigenvector and mu is the eigenvalue and J is the matrix, obviously. So this is just the definition. And when we substitute in our matrix J plus 29i into this, we get this equation. And if we get this equation, we're just basically distributing the V. So then we get J times V plus 29 IV. Since IV is just basically V because the identity matrix doesn't do anything, then we can just know that it's just still JV plus 29 IV V. And since we know that J is equal to mu, then we can get mu V plus 29. So then we can just factor out the V and we get mu plus 29 V. So that's basically what it means by shifting by 29. The eigenvalue by 29 is just over here. We see that's shifted by 29. So it's still essentially the same, but it's added to 29. And then the second question that I didn't really explain earlier was how do we get the eigenvalue 30 and 0? 0 and 30 are pretty straightforward. 0 is pretty straightforward because we know that it has rank 1, so there's definitely a no space, so 0 is one of the values. That's a no-brainer. 30 is because if we consider like adding up, summing up the things, then we would have something of the form JV equals lambda V. And then we have a mu, let's say, of just the transpose of just a bunch of ones. If we times J and U together, we would have this. And basically that's what this is doing, is just adding up the sum of each row. And since we have 30 rows, I mean 30 entries in each row, the result is 30. So we have in each one we have 30. And we can factor it out to get 30u. So then JU is equal to 30u, so 30 is an eigenvalue. So that's why we have 30 as an eigenvalue. So then once we get 0 and 30, we would just plug it back to the 29 shift. So then we would get our 59 and 29 as earlier with 29 repeated 29 times and 59 repeated once. So that's the geomultiplicity. So then we would just do lambda plus g, that's basically the square. So then we get 59 plus 1 is 60, 29 plus 29 is 58. Square the two, we get 6964. So that's basically it. I definitely learned a lot from this. Definitely a lot of review for me of what it means by the shifting and what the equation A V equals lambda V means. Like, I know that expression, but I definitely didn't think of it. And 30 kind of came to me as a surprise because obviously there should be a matrix of 1, 1, 1, 1, 1, and 1, 1, 1, 1, 1, like basically that. But I just didn't think of. Okay, that's it for today.